All right, let's get started. Let me share my screen. Okay, so we're continuing our discussion of thermochemistry in chapter 6. And now we're going to get into how we do calculations based on measured values using calorimeters, all right? So if you remember, we talked about the calorimeter, which is basically what is used to measure heat flow in any process, chemical or physical. And basically, if we're dealing with a chemical reaction, then there's a relationship between the heat change of the reaction itself and the heat change experienced by the calorimeter, right? So that's the equation right here. Q for the reaction is equal to minus Q of the calorimeter. And that's it, right? Because if the reaction, let's say, is exothermic, that means that as far as the reaction is concerned, Q will be negative. But as far as the calorimeter is concerned, which is absorbing the heat, Q would be of the opposite sign. So that's why we have this relationship right here. So basically, we can write down that the Q of the calorimeter will be equal to mass times specific heat times the change in temperature of the process, right? Okay, so based on this, we can determine the enthalpy change. And the next slide is an example of a question where it demonstrates how this is done. So again, I'm going to need, I'm going to need some space. Copy this and paste it in the document. Okay, so that's a question, right? It says you have a 50 ml sample of 0.250 m hydrochloric acid, excuse me, at 19.50 degrees Celsius is added to 50.0 mils of 0.250 m sodium hydroxide, also at the same temperature in a calorimeter. After mixing, the solution temperature rises to 21.21 degrees Celsius. Calculate the heat of this reaction. Okay, so basically what we have to do first is determine the amount in moles of each of the substances, the acid and the base, right? So they gave you the volume, which is the same for both the acid and the base, and they gave you the molarity, which is the same for both the acid and the base, right? So basically we can say that the number of moles of the acid that we're going to calculate will be equal to the number of moles of the base, which is the sodium hydroxide. And that would be equal to 50.00 mils, which we have to convert to liters. So 1 liter over 1,000 mils. And then we multiply that by 0.250 m. So that's 50 divided by 1,000 times 0.250. So according to my calculation, this comes out to be equal to 0.0125 moles, right? So the moles of the acid and base are both the same. Now there's one, let me see here. Okay, so we have to determine the mass of the solution. Now, when it comes to aqueous solutions, such as in the case of hydrochloric acid and sodium hydroxide, we can assume, and I probably should have included that statement in this question, assume that the density of the solution is equal to 1.00 grams per mil, all right? Which is the density of water. And for most relatively dilute solutions, that's the case, right? So if we determine that to be the case, then we can say that the mass of the solution would be equal to, okay, so the total volume here is 100 mils, 100.0 mils, multiplied by the density, which is 1.00 grams per mil. And then we're going to multiply that by the specific heat. So that's another assumption that we're making. We assume that the specific heat of the solution, when you mix them, is equal to the same as water, 4.18 joules per gram degree Celsius, right? So that should be another piece of information that should have been included in this question. So let me correct this here. So this would be 4.18 joules per gram degree Celsius. And then we multiply by the temperature change. What's the temperature change? Well, the final temperature is 21.21. The initial temperature is 19.50. So 21.21 degrees Celsius minus 19.50 degrees Celsius, right? So that would be the mass of the, well, actually, I need to correct this here. The first part here represents a mass, but what I'm calculating here is actually the Q of the, this would be the Q of the calorimeter. All right. So let's do that calculation. So that would be 100 times 1, which is 100 again, times 4.18 times the difference between 21.21 and 19.50. And according to my calculation, rounded out to 3 sig figs will give you 715 joules, because this will cancel out here and here, the grams will cancel out here and here, degrees Celsius cancel out here and here. So the final unit will be joule, right? So this is the amount of heat that the calorimeter will absorb, which means that Q of the reaction will be equal to minus 715 joules. All right, because again, Q of the calorimeter will be equal to minus Q of the reaction. All right, so that answers the first question on this slide right here. All right, now the next question is asking for you to express the result of the previous question for molar amounts of the reactants and products. That is, determine the value of the delta H that should be written in the equation right here, right? And the way we would do that, going back to this right here, is that we would take the minus 715 joules and divide it by the moles of each of the components or each of the reactants, which we calculated here. So that will be over 0.0125 moles. And then we do that calculation. So 715 divided by 0.0125. And according to my calculation, when rounded up to 3 sig figs, you're going to get 5.72 times 10 to the 4, I'm sorry, and joules per mole would be the units, all right? So therefore, this number that we have here should be written where it says delta H equal, all right? So delta H would be equal to 5.17 times 10 to the, so it should be 5.17 times 10 to the 4 joules per mole. And that's it. So that's how you do that. All right. Okay, any question about this? Any questions? All right. So I think we discussed the bomb calorimeter before. But what this is talking about is that in the case of the bomb calorimeter, if you remember, I said that we use this particularly for organic compounds to find out the heat of combustion of organic compounds. And this is the setup that you see here. I went through that before, so I won't go through, describing the setup again. But basically, in this particular case, the measurements are done under conditions of constant volume. In other words, the volume doesn't change, right? So therefore, in that case, the Q of the reaction or minus Q of the reaction will be equal to only the change in internal energy. Or I should say, will be equal to the internal change in internal energy. So basically, that's how that is done. And therefore, as a result, the change in internal energy will be a good approximation for the change in enthalpy of such reactions. Okay, so now we're going to get to Hess's law, which is what's important for you to do questions. Let me see here. Question, I think it's a remaining question that we have not gotten to yet in this assignment 6. Okay. So Hess's law, very important law, a very useful law, especially when it comes to determining the enthalpy change of reactions, which are very difficult to measure. All right. So basically, some reactions cannot be carried out, right? For many reasons. All right. And therefore, because these reactions cannot be carried out, at least conveniently, we cannot determine delta H directly. However, we can determine the delta H of such reactions if we have data delta H value or values for other related reactions, all right? So let's consider this reaction, the reaction between carbon and oxygen to form carbon monoxide, right? Now we know this reaction occurs, but it's very difficult to carry out experiments based on this equation to determine delta H. And the reason why is that the carbon monoxide, as soon as it is formed, it will react with more oxygen, and therefore carbon dioxide will be produced, right? So therefore it's very difficult to just take carbon and react it with oxygen and you just get carbon monoxide, because the carbon monoxide will itself continue to react to form carbon dioxide, right? So the question now becomes, how do we determine the enthalpy change of this reaction here, right? So this basically is based on the fact that the enthalpy change is a state function. And therefore the state function, like any other state function, it doesn't matter how you get from the reactants to the products, it doesn't matter how many steps you take, that value, the net change would be the same. So that is true for enthalpy, right? The enthalpy change of a reaction is the same, whether or not the reaction is carried out in one step or more than one step, right? So basically that's what Hess's law is all about. It says that if an equation can be expressed as a sum of two or more other equations, then the enthalpy change for the desired equation is the sum of the enthalpy changes of the other equations, all right? So that's Hess's law. And Hess's law is actually directly coming from the conservation of energy law, right? Basically what they're saying is that it doesn't matter how you get from reactor to product, basically the amount of energy that it takes in terms of the enthalpy would be the same. So energy in this context cannot be created or destroyed. All right. So let me before we get into this real chemistry example, let me just give a hypothetical example. So let me go to this right here. So let's say it is possible for you to go from A. Let's say it's possible for you to go from A to C, right? But it is also possible for you to go from A to form B, and then B will react to form C, right? So I'm going to call the enthalpy change for A to B, I'm going to call that delta H1, right? And then going from B to C, I'm going to call the enthalpy for that delta H2, and then going from A to C, I'm going to call that delta H3, right? So what Hess's law is saying is that it doesn't matter if you go from A to C or you go from A to C through an intermediate B, the total energy change will be the same. The total enthalpy change is going to be the same. So therefore, we can write down a relationship between delta H3, delta H1, and delta H2, and that is delta H3 is equal to delta H1, 1, plus delta H2, right? So that's basically what Hess's law is saying, right? And this is convenient if, for example, let's say, experimentally speaking, it's very difficult to determine delta H3 but you know what delta H1 and 2 is, right? So basically all you can do is add delta H1 to delta H2, and that will give you delta H3 without carrying out the experiment to determine directly delta H3, right? So that's basically the utility of Hess's law. Now let me show you another way of approaching this. Let's say I write down this, A going to B, and the enthalpy change for that is delta H1, and then from B going to C, the enthalpy change for that is delta H2. Now, you know from previous experience, and I think we discussed this when we were talking about net ionic equations. If you're adding two or more equations together, you cancel out common items on both sides, right? Which in this case would be the B, right? So if you cancel out the B's, you're going to end up with A going to C, and that would be equal to delta H3. And to get the value of delta H3, we add these two. So that would be delta H1 plus delta H2, just like we did up here, right? So these are just two different kind of approaches you can take in order to see the relationships between the different enthalpy values. Okay, so with that said, let's apply this now to the reaction where we're trying to find the enthalpy change going from carbon to carbon monoxide. So let me just, okay, so basically this is what we're trying to find, right? But we know we can determine experimentally going from carbon monoxide to oxygen to form carbon dioxide. That has been determined, and that's the value right here, minus 283.0, right? It has also been determined that the carbon reacting with oxygen to form carbon dioxide give this value, right? So we know that this value here, based on Hess's law, would be the sum of these two. So therefore, to find this value, we would have to find the difference between minus 393.5 and minus 283.0. And if you do that calculation according to what I have here, the answer will be equal to minus 110.5. Minus 110.5. So that's basically how, and this will be kilojoules. And that's basically how we can exploit Hess's law to determine the enthalpy change of a particular reaction if we know the data for other reactions that are kind of related to it. Okay, so here's an example. This is a typical enthalpy change reaction. So the question says you have to calculate the enthalpy change for this first equation right here, right? And they gave you these three equations along with their corresponding enthalpy change values. So I'm going to need space again. So let me copy and paste this. Into this Word document here. So let me delete this here. Again, this. Okay, so this is a question, right? Okay, so like I said, your aim is to determine the delta H for the first equation, and they gave you these values, all right? So this is the approach that you take in order to solve a problem like this. What you do is compare each of these equations for which the delta H values are known to this first equation here and make certain changes. So let me explain using the first one here, right? The B equation. So basically, I'm going to compare this equation to this equation, and what I notice that they have in common is that you have carbon on the left side in both cases. But the difference is that you have a coefficient of 2 here for this carbon. So what I would do is that I would multiply this entire equation here by 2. If I'm going to do that, that means that I have to multiply this value as well by 2, right? So let's do that. So 2 times carbon solid, I'm just going to leave out the graphite wording, plus 2 O2 gas, and state symbols, by the way, are very important. So you need to include them as well, to give 2 CO2 gas, right? And that means that the delta H value for this would be equal to 2 times minus 393.5 kilojoules. So let me see what that gives. 393.5 times 2. So according to my calculations, this works out to be equal to minus 787.0 kilojoules, all right? Okay, then we compare the next equation to the first one, right? And what do we notice that they have in common? They both have C2H4, but the difference is the C2H4 here is on the left, while the C2H4 here is on the right side. So what we're going to do with this equation here is that we're going to flip it, right? So basically, to flip it, you're going to end up with 2 CO2 gas plus 2 H2O liquid to give C2H4 gas plus 3 O2 gas, and delta H now would be equal to the reverse, because remember, when you flip the equation, what happens to the sign of delta H? Exactly. So therefore, instead of minus 1410.9, this would be positive 1410.9 kilojoules. All right. Okay. So now we get to the last equation here. So when we compare this equation, the last equation, to the first one, what do we notice? They have in common H2 on the left side. But the difference is there's a 2 here, a coefficient of 2 here, and there's 1 here. So what do you think we do with this? What's that? We multiply by 2, exactly. So when you multiply this by 2, you're going to end up with 2H2 gas plus O2 gas to give you 2H2O liquid. And what happens to the delta H value? What happens to the delta H value? If we multiply this equation by 2, what happens to this?
It's also multiplied by 2.
We're going to multiply by 2 as well. So 2 times minus 285.8 kilojoules. So let's see what that gives. 285.8 times 2. And that gives you, according to my calculation, please check to make sure I'm doing the right thing, because I am, of course, only human and I can make errors, all right? So please check up on what I'm doing and please feel free to correct me. But this is what I got here, right? Okay, so now that we have multiplied and did all the changes that we need to make, then what we're going to do now is add these equations together, all right? And of course, again, as I said before, when you add equations together, then we cancel out items that are common to both sides. So let me hear what you think will be canceled out when we add these 3 equations together. We're looking for identical items on both sides of the equation. So what do you think is going to cancel out as a result of that?
CO2.
CO2s will cancel out. These 2 will cancel out with these 2. I would agree with that. Anything else?
H2O.
Okay, yeah. These 2 water molecules in a liquid state will cancel out with those 2 water molecules. Anything else?
The oxygens cancel.
The oxygens will cancel because you have a total of 2 plus 1, 3. So these 3 oxygens will cancel out these 3 oxygens. So let's write down what we're left with, because there's nothing else to cancel out. You're left with 2 carbon solid plus 2 H2 gas to give C2H4 gas, which is the same as the original equation here, right? So what does that mean for the delta H that we're going to calculate here? Delta H here would be equal to the sum of these numbers that we obtained here, right? So that would be 787.0 minus, and then we add to that 1410.9, and then we add to that minus 571.6. And then according to my calculation, and again, please check up on this to make sure I did the right thing, but I got 52.3 kilojoules. All right. And that's a typical Hess's law question. In fact, I can guarantee that at least one question like this will come in your Not this test, because this test is only chapters 3, 4, and 5, but the next test, right? So I can guarantee that at least one question like this will be in that test, maybe more than one, but at least one, all right? Okay, any question about this example? Any question? Any questions? So let's go to the assignment, because in the assignment, there is at least 2 questions or 3, if I remember correctly. Okay, so let me go here. Let me go here. And then assignment. And then chapter 6. Okay, so let's see here. Scroll down. Okay, here we go. First one, right? Very similar to what we just saw. They gave you an equation. They're asking for the delta H for that equation, and they gave you 3 other equations. All right. Okay, so let me hear what you have to say about solving this. All right. So let me hear ideas. How would you go about, based on what we did in the previous example, how would you go about starting to solve this problem? Remember what you're going to do. If you remember what we did the last time in the example, we compare each equation to the one that you're trying to find delta H for, right? So let me hear what you have to say. And you guys out there in Zoom, let me see who's out there. Addison and Jack, feel free to join in and make your contribution to today's class. All right, so let me hear your ideas.
We can multiply first equation by 2.
Okay, why would you do that? Let me hear your reasoning.
Like, we can multiply first equation by 2 because it's 2NO and then it's 4NO.
Okay, right, because you have 4NO here
Yeah,
and you have 2NO here. So I would multiply, you're correct. I would multiply this by 2. So when you do
But-
that,
we can also multiply it by 5 because it's 5O2 and O2.
okay, stick up in. I'm going to say something about that. I'm going to say something about that because that's a common error that students sent to me. I mean, I understand why you say it, but not quite right. But let's go ahead and multiply by 2. The first equation. So if you multiply that by 2, you're going to end up with 2N2 gas plus 2O2 gas to give 4NO gas. All right. And what happens to the delta H value as a result of that? It doubles. So therefore, 2 times minus 180.5 kilojoules, which works out to be minus 361.0 kilojoules. All right. Now, going back to what Ms. Patel was saying, she was talking about the fact that you have 5 oxygens here, and she was suggesting that you multiply this by 5, right? The problem is that you have oxygen, you have an oxygen right here. If you have one particular compound or substance or element in more than one equation, you don't multiply those by anything, right? In fact, those will work out in the end as you're going to see, right? So you only try to multiply, if you need to, those elements or those substances that appear once in each equation. You see what I'm saying? Okay. Now, what next? What next? What would be your next step?
Or the next one by 2 as well because of the ammonia.
Well,
Also flip it.
also, I was about to say, you have to do 2 things. You have to multiply by 2 and you have to flip it, right? So I'm going to write here, multiply by 2 and flip, right? So when you flip it and multiply by 2, you're going to end up with 4NH3 gas to give 2 N2 gas plus 6 H2 gas. And what do you think is going to happen to the delta H value here as a result of both multiplying by 2 and flipping? So we're talking about this value here. What's going to happen to it?
It's gonna double.
You're going to double,
It's gonna be positive.
and the sign will change, right? So that will be positive 91.8 kilojoules. So let's see what I get. So 91.8 times 2. So according to my calculation, this works out to be equal to 183.6. All right. Okay. What next?
The third equation by times 3,
Exactly. Why would you do that? Because
because it's 2H2O and 6H2O.
you have 2 water here, you have 6 water molecules here. So this time, for this equation, I multiply this by 3. So that would give you 6 H2 gas plus 3 O2 gas to give 6 H2O gas. All right. Okay. And what happens to the delta H as a result of that? What happens to the delta H value as a result of multiplying that equation by 3? It triples. So 3 times minus 483.6 kilojoules is what you're going to end up with. Let's see what that gives. So 3 times 483 minus, so according to my calculation, this gives 1449 minus 1449, right? Kilojoules. All right. So that means now we can add everything together, right? And remember again, when you're adding, you will be canceling those items that are common to both sides. So what would those items be in this case?
Nitrogen.
Yep, correct. The N2 here and here. Anything else? The hydrogens. Yep. Anything else? I don't think so. Yeah, I think those are the only items that would cancel. So we write down what's left. And what is left? 4 NH3. And notice the oxygens. You have 2 oxygens and 3 oxygens on the same side. So those won't cancel. Those would add up, right? So you're going to end up with plus 5 O2 gas, and this is a gas, by the way. And then on the right side, you're going to end up with 4 NO gas plus 6 H2O gas, right? And that will be the same equation as the one for which they're asking for you to calculate delta H. So which means that to get delta H here, we add up all these values over here. So let's do that. So that would be 361 minus plus 183.6. And then I'm going to add to that minus 1449. And according to my calculation, that works out. Now this I have to round out to 0 decimal places. So that will equal to minus 1626 kilojoules. That's what I got. All right. Any questions about this one? Any questions? So again, this is a typical Hess's law type of question. Very typical. All right. No questions? Okay. Let's clear this here. And let's scroll down. Okay, let's see. Let me hear what you have to say about this one. Again, they gave you one equation and they gave you for which you're asked to determine delta H, and then you're given three equations and their corresponding delta H values. Okay, so let me hear your ideas about this one. How would you go about, what would be the first step in solving this problem? Well,
First equation remains same.
exactly, because you have C2H4 here, C2H4 here, and it's 1 on the left side, so I'll just rewrite this equation here. C2H4 gas plus 3O2 gas to give 2CO2 gas plus 2H2O liquid. And delta H for this is equal to, delta H is equal to minus 1411 kilojoules. Okay, next step.
Flip the second equation.
I'm sorry?
Flip the second equation.
Exactly, because in the case of the second equation, you have C2H6 on the left. Here in the original equation, it's on the right. So I would flip it. So when I flip it, I'm going to end up with 2 CO2 gas plus 3 H2O liquid to give C2H6 gas plus 7/2 O2 gas. And what happens to the delta H?
It becomes positive.
Right, so the answer would be 1560 kilojoules. The sign changes. Okay, very good. One next.
You just keep the same.
Yeah, get the same.
I'm sorry?
Keep the same for the third one.
You mean flip this one? Well, not only should you flip it. Hold on, let's see here. Oh,
It's the same.
sorry, it should remain the same. Okay, yeah, my bad. I don't know what I was thinking. So just rewrite it. H2 gas plus half O2 gas to give H2O liquid. Right? And delta H for that would remain as minus 285.8 kilojoules. Okay, very good. So what do we do next? Add these up. So let's see, what will cancel out?
CO2.
Okay, yep. Anything else? Yep, because these 3 water molecules will cancel out these 2 plus 1 on the right side. Anything else? Or is that it?
The oxygen.
Yes, the oxygens. 3.5, 7/2, same thing, right? And I think that's it. Okay, so basically, we just write down what's left, which is C2H4 gas on the left side, and then on the plus H2, sorry, plus H2 gas to give C2H6 gas. And let's find out what delta H is equal to. So that's 1411 minus plus 1560, and then minus 285.8. Oh no, I did something wrong. Okay, I'm gonna do say 1411 minus plus 1560, and then minus 285.8. Okay, so I got -1, and again, I have to round up to know decimal place. So 1 minus 137 is what I got. Kilojoules. And that's how you do that. All right. Any questions about this one? Any questions? Okay. So let me go back to oh my God. Okay, so let me clear this here. Oh, confusing myself. Okay, okay, so here's another one. What I'm gonna do is leave for you to do. Take the same approach as we did in the previous two. So I'm gonna leave number 11. Oh, that's it. Okay, so number 11 is the last one on this. However, I remember there was an addendum that I added. But let's go to the PowerPoint first, and then I'm going to get to the questions in the addendum part. All right. All right. So that's Hess's law. Now let's talk about what we call standard enthalpy of formation, because enthalpy values that you'll obtain from an experiment is dependent on conditions applied, or the conditions under which these measurements are taken. Conditions of temperature and pressure especially can change the enthalpy values. So therefore, what was decided, again by the powers that be, is that basically we assume certain conditions to be standard conditions. Now this is important because in order for us to calculate the enthalpy change by definition, you need the total enthalpy of the products and you subtract from that the enthalpy of the reactants, right? In other words, you need to know the absolute enthalpy of these substances. The problem is we cannot measure the absolute values of enthalpy. So therefore, what we have to do is use a relative scale. And that's the reason why we need a standard state or standard conditions in order to basically have a level playing field, so to speak, so that we can determine the enthalpy changes for different reactions, right? So the standard condition that was defined by the powers that be was that if there are any gases that are present, then the pressure of those gases would be 1 atmosphere, and the temperature for all the substances involved would be 25 degrees Celsius, right? So therefore, once those conditions are set and you measure the delta H based on those conditions, that enthalpy change, that delta H value, is called the standard enthalpy change. And that is symbolized by this symbol right here, delta H with a small o or 0 as a superscript. So whenever you see that, you understand, or you should understand, that the enthalpy changes that are indicated or measured and expressed are measured under standard conditions. 1 atmosphere pressure for gases involved, and the temperature will be 25 degrees Celsius. And there are some other standards, there are some other conditions as well. The molarity of any aqueous solution will be 1 molar, and I think that's it. Yeah, all right. Okay, so basically that's the standard enthalpy change. Now there's another term which is called the standard enthalpy of formation, right? Again, the same conditions apply, but this basically is referring to a situation where you form 1 mole of the compound from its constituent elements under standard conditions, right? So basically that equation, the enthalpy change for that equation, is called the enthalpy of formation under standard conditions, or standard enthalpy of formation. All right. Okay. Now here's an example. So let's say, for example, we want to express or find out the enthalpy of formation of this compound, methanol, right? So what we do is write down the equation for the formation of 1 mole of methanol, right? So in other words, you start off with 1 mole of methanol here, and you know that it's made up of carbon, hydrogen, and oxygen, right? So therefore, if you set the coefficient here to be equal to 1, you balance the equation based on that condition, right? The fact that you're going to end up with 1 mole of methanol, right? So that's why you see that you have 1 mole of carbon, 4 moles of hydrogen, and half a mole of oxygen coming together to form 1 mole of methanol. So basically, according to the information provided here, for this reaction to take place, to form 1 mole of methanol, the enthalpy value is minus 238.7 kilojoules under standard conditions, 25 degrees Celsius, 1 atmosphere pressure, and therefore this delta H standard for this reaction, the enthalpy of formation standard for this reaction is minus 238.7 kilojoules, all right? So that's basically how we determine the standard enthalpy of formation of methanol, and that can be applied to pretty much, this process can be applied to pretty much any compound, right? Now, basically, because we have that standard, and because we can measure the enthalpy of formation under standard conditions, we can actually treat them as if they're absolute enthalpies, and therefore we can use those to calculate the standard enthalpy change of different reactions, all right? Now, here's an interesting question. This question is asking, what is the enthalpy of formation of an element in a standard state, all right? And the hint is, the reactants will be the same as the products. In other words, let me squeeze it in right here. In other words, O2 gas to form O2 gas, right? What's the enthalpy of that? Enthalpy of formation, standard, that would be equal to what?
0.
Exactly, right? So for any element that exists in nature in their natural state, the enthalpy of formation of those elements are 0, all right? So that's true for oxygen, that's true for bromine, that's true for sodium, that's true for all the elements that exist in the periodic table, all right? Okay, now, based on those values, we can, as I said before, determine the standard enthalpy of reactions based on the standard enthalpy of the formation of each compound or each substance involved in the reaction. And basically the way we do that is by using this equation right here, which might look a bit confusing, but it's actually quite simple, right? The enthalpy change of reaction would be equal to the sum of the enthalpy of formation of the products minus the sum of the standard formation of enthalpy of formation of the reactants, right? So basically this delta HF, and we have products here, that's the standard enthalpy of formation of the products, and this Greek symbol mu is basically the coefficient of each substance. And of course, I don't know if you're familiar with this symbol, sigma in math, that means sum of. So basically what this means is that you're adding all the enthalpy, all the standard enthalpy of formation of all the products, and then you're going to do the same thing for the reactants, and then you're going to take the total of the reactants and subtract it from the total of the products, right? And that's basically it. And this is more convenient, especially since it will be more complicated if you were trying to use Hess's law. Hess's law can work, but it will be a bit more complicated. More steps will be involved. And so the question is, how do we get these values? Well, there are tables that are provided, and in fact, I provided a table in Canvas, which you'll have access to during your test, and just show you what the table looks like. Where is it? Where is it? Okay. I could have sworn I had it here. I would have to, I thought I uploaded it. I guess oh, let me go here first. Here it is. All right. Okay, so this is a table which gives you the standard enthalpy, the standard enthalpy of formation of different substances. There are some other information given which for this course you won't be using. You won't be using this column here, which is dealing with free energy of formation, nor are you going to use entropy, right? For those of you who have to do Chem 2, you're going to be using these, but not for this course, right? For this course, you're only using the first column right here, right? So remember I said for any element, the enthalpy of formation is 0, right? Well, that's what you're going to see in this table, right? For all elements by themselves, not combined with anything. The free element under normal natural conditions, the enthalpy of formation is 0. So that's true for aluminum, that's true for antimony. I'm sorry, not antimony, arsenic. That's true for barium, that's true for boron, that's true for bromine, all elements, calcium, all free elements, they all have the same value, which is 0 for the enthalpy of formation under standard conditions, right? So basically, these are the values that you're going to use to calculate, if you're given a question where you're asked to calculate the enthalpy of a reaction under standard conditions, you're going to use these values. And in the PowerPoint, there's one example here, right? So let me copy and paste this again. And let me go here, here. Let me lasso this here. Okay, so this question says, it gives an equation, and basically they're asking for you to calculate the standard enthalpy of formation. And you're going to use the data from the tables, right? So basically, to find delta H, of the reaction, standard, that would be equal to 4 times the enthalpy of formation under standard conditions of carbon monoxide gas, plus 8 times the enthalpy of formation of hydrogen gas. All right, and those are the products. So I'm going to surround them with square parentheses. And then now I'm going to look at the reactants, minus the sum of the 3 times the enthalpy of formation of methane, CH4, plus 2 times the enthalpy of formation of H2O liquid, plus the enthalpy of formation standard of carbon dioxide gas. All right. Okay. And then I'll put that in square parentheses together. So what we have to do now, see if I can share both of these on the same screen. That should make it smaller. Okay. You see, what I want to do is look up the values. Move this over here. Let me minimize that. This here. Okay, let me try to work with this. Okay, so what I would do is go to the tables and look up the values for carbon monoxide and all the other compounds. Now, I can simplify things a bit because of what I said earlier. I said that for any element by themselves, the enthalpy of formation is 0. So therefore, I know that for hydrogen by itself, that would be 0. So 8 times 0 would give you 0. So I'm just going to put 0 right here. So now what I have to do is look up the value for carbon monoxide. So let me scroll down. Carbon monoxide, where are you? Okay, carbon monoxide, the value here is minus 110.53. So I'm going to put 4 times minus 110.53 kilojoules, right? And then on the other side, I'll be looking for methane. Now, one thing I should say about this table, at the very end, I think the last 2 pages, they have a special table for organic compounds, and methane is organic, so that's why I'm scrolling all the way down here, right? For methane, the enthalpy of formation is this right here, minus 74.81. So I'm going to put that here. 3 times minus 74.81 kilojoules. And then I'm going to add to that 2 times the enthalpy of formation of water, liquid. So let me see here, water, where are you? Oops. There you go. Water. Okay, water, liquid. And by the way, pay attention to the state because the enthalpy of formation is affected by the state, right? So we look specifically for water in a liquid state that is minus 285.3. So that will be 2 times minus 285.3 kilojoules, right? And then finally, we look up the value for carbon dioxide. So here. Carbon dioxide gas, which is minus 393.51. So minus 393.51 kilojoules. All right. And then we do the number crunching. So I'm going to work out this part first. So that is 110.53 times 4. And according to my calculation, that works out to be equal to 442.12 kilojoules. And then that's 0, so that takes care of that. And then on the other side, I'm going to work out the rest of this. So this will be 3 times minus 74.81. And then I'm going to add to that 2 times 285.3 minus. And then I'm going to add to that minus 393.5 minus. So this part here, according to my calculation, works out to be 1 minus 118.5. You round out to 1 decimal place. Kilojoules. And then we do the final calculation. 442.12 minus, so that's plus 118.5. And I got, oh, no, something's wrong here. This is 442.12 and then plus 118.5. So I got 1630.6. 1630.6 kilojoules. And that should be your final answer. All right. And that's how you do that. So based on this, the questions that is given on the addendum page, you should be able to do that, right? So you're going to need this table. Did I publish it? Let me check and make sure I published that table. Let me see. Okay, it's published, right? So you can use that, use those values. Make sure you use those values from that table to answer the questions in the addendum section of the assignment. Okay, and that's pretty much it for chapter 6. All right. Oh, there's another example here. You can look at this example as well. It's a similar approach. The only difference, let me just say something about this. The only difference is that in this example here, they gave you delta H, right? For the reaction. In this case, you're asked to find delta H standard for the reaction. In this case, they gave you delta H standard, and they're asking for you to determine the enthalpy of formation of isopropyl alcohol based on that delta H value and also the enthalpy, the standard enthalpies of the other components or other substances involved in the reaction. Okay, what time is it? 11:01. All right, so that's basically it for this chapter. So now we're going to move on now to chapter 7. And chapter 7 is dealing with the atomic structure. There are some things that you'd have met before, but in your introductory chemistry or high school chemistry, but we're going to delve into some other related topics in more detail. So let me get to that PowerPoint. Chapter 7, the atomic structure. All right. Okay, so firstly, I just want to give a very brief historical review of how we arrived at our current understanding of the structure of the atom, right? So at first, people thought back then, and I don't remember the dates or years, but way back when, people assumed that, okay, atoms exist and other particles exist, maybe, but it was assumed that the way these particles behave would be pretty much the same way as normal sized objects, right? So basically normal sized objects, their behavior is governed by Newtonian laws, right? So they believed back then that atoms basically behave the same way, and not only atoms, but other small particles as well. And then some experiments was done with light. We're going to get into some of that later on. And it was found out that that's not the case. So therefore, a new idea was put forward to explain the behavior of small particles, and that is called the quantum theory. And therefore, based on the quantum view, we now have a better understanding of how electrons behave, especially when they're located in atoms, right? So to start off this discussion here in terms of the historical view, somebody by the name of Johann Hittorf in 1869, he discovered what was called back then cathode rays. And this is actually a stream of electrons. So here is a diagram of the setup of the discovery of these rays. You have two metal electrodes, and they're connected, hooked up to an electricity source, right? One is called the anode because it is positively charged. The other one is called the cathode because it's negatively charged, right? And basically this tube was evacuated, right? So there's no air in it. And then they flipped the switch, and what they noticed was that there's a stream that emerges from the cathode and is attracted to the anode, all right? And the first thing that one can conclude based on this observed is that the nature of the stream of particles is that they must be negative, because they're leaving the negative electrode, which is the cathode, and moving towards the positive electrode, which is the anode. Some other things were discovered about the stream of particles, because this is what happens in science. I don't know if I've mentioned this before, but whenever there's a new discovery, then all scientists try to rush and see, okay, what can we investigate, know about, this newly discovered phenomenon. And that's what happened in this case, right? So, people try to play with it, and they discovered that the cathode rays that were produced in that experiment can be deflected by the presence of an electric field, and also can be deflected by the presence of magnets. So this is an example here of the same setup here, and whoops, the magnet is placed down here, right? And as you can see, the particles are directed towards the magnet, all right? Some other properties that were discovered was that when these particles hit certain materials like glass and other materials, they fluoresce, which basically means that they light up or shine or whatever you want to call it, all right? So those are just some initial discoveries that were made in relation to these newly discovered cathode rays. So J.J. Thomson was one scientist who was very interested in delving more quantitatively into the nature of these particles. So he set up an experiment which is basically some other things added to the original experiment, right? And this is a diagram which represents what he did, right? So just to explain to you the different parts here. So the entire tube is evacuated first, right? And then you have the cathode here, which is connected to the electricity source. And then this here serves as an anode. But what he did was that he made a slit through the anode so that the stream of particles produced here, some of them will pass through here as a beam. And then to make the beam more focused, he provided another part here, which has a slit, and that allows the beam to pass through. And then what he did in this part of the apparatus, he arranged an electric field, which is set up as a result of these two plates here and here, themselves connected to an electricity source. So what he could do is vary the electric field and see how it affects the movement of the stream of particles, right? If he adjusts it one way, they may go up. If he adjusts it another way, they may be deviated down, right? He also, in this region, placed two magnets right here, right? And he could adjust the strength of the magnetic field and polarity, again, causing deflection, right? So that's the setup here. And then finally, at this end here, you have a scale, which basically measures the angle of deflection, right? So if the magnetic field and the electric field were turned off, the beam will just go straight through without being deflected. But if he plays with the electric field or plays with the magnetic field, then he can deviate or deflect the beam, and therefore they can move up or down, all right? So that's the setup. And then he did some calculations in relation to this, which fortunately for you guys, you don't have to get into. I remember because when I was in school, I majored in physics. We actually had to do the calculations to show what he discovered, right? And just to give you the result, the final result of what he did based on the calculations, he determined the mass to charge ratio, the mass of the particle in relation to the charge of the particle, right? And that was what he discovered. The mass to charge ratio of the particle is minus 5.686 times 10 to the minus 12 kilograms per coulomb. So that's basically the result of that experiment, all right? But of course, scientists are not satisfied with this. I mean, even though this was a very important step in terms of investigating the nature of these particles, but of course, scientists are not satisfied because they want to know what the mass is and what the charge is, right? So the mass to charge ratio, well, that's a good discovery that he made. That's not enough to satisfy what scientists tried to find out. Now, the particles that were responsible for that stream in that experiment were named electrons, right? So this guy, Millikan, he came up with another experiment, his famous oil drop experiment. And again, there's some calculations involved, which again, you guys don't have to be worried about. But let me just briefly describe qualitatively what is happening in his experiment. So basically what he has here, he has two plates, again, connected to an electricity source. So this is the cathode, this is the anode, right? He also has a source of ionizing radiation. He also has a very small hole that is punched through the cathode plate, right? And he sprayed an oil. Now, I'll be honest with you, I don't remember what kind of oil it is. I think it's some sort of hydrocarbon. In any case, he sprayed a fine mist of oil onto the cathode plate such that droplets of the oil can pass through the plate. Now, here we have the ionizing radiation. What that does is that it knocks off electrons of the drops, right? So now we're dealing with a charged oil drop, right? And because the oil drop is charged, we can now suspend that oil drop between the plates, right? Because there's an electric field right here, right? And he did some calculation. Again, this is something that I remember doing in physics, but basically, based on the suspension of the oil drop between the two plates, and based on the mass of the oil drop in conjunction with the size of the electric field between the two plates, we can find out what the charge on the electron is. And he discovered that the charge on the electron is minus 1.6 times 10 to the minus 19 coulombs, right? So if we know the mass to charge ratio, which is what J.J. Thomson discovered, and Millikan now discovered the actual charge, then to get the mass of the electron is very simple. You multiply the charge by the mass to charge ratio. So basically, based on that, we end up with the mass of the electron being determined to be 9.109 times 10 to the minus 31 kilograms per electron. So this is basically how we know both the mass and the charge of the electron. Okay, now, hold on, let me see something. Okay, now J.J. Thomson, taking into account all that was known back then, he came up with this famous plum pudding model, which is basically the model that that he proposes, which represents how the atom is, how the electrons are arranged in atom. So he proposed a model where you have a large, relatively speaking, sphere, which is positively charged, and then you have electrons embedded in that sphere and equally spaced, right? So for example, he proposed that for the hydrogen atom, there's only one electron, and that electron will be sitting right in the middle of that large, relatively speaking, sphere, which is positively charged, right? And then he proposed that in the case of helium, which has 2 electrons, the 2 electrons are embedded in a large sphere, but basically the electrons are spaced evenly along a straight line to the center, right? Where each electron is halfway between the center and the outer surface of the sphere, right? So basically this is his model of the helium atom. And he suggests that if you remove one of these electrons from here, then the remaining electron will simply move to the center, right? So that's his model. In some textbooks, they call it the plum pudding model or the raisin pudding model, right? So that's the idea that he came up with, okay? Now, of course, again, people are not just satisfied with, somebody coming up with an idea, as reasonable as it may sound at the time. Okay, what happened here? Okay. I have left the meeting, they say. I don't think so. Let me try to reconnect. Let me see. Okay, I am back. Okay, and I need to hold on, let me see if sharing my screen. Oh, I can't share my screen. That means I need to. How do I do this again? How do I do this again? Okay. Oh, okay. Now I'm business. All right. So let me go back to the PowerPoint. Okay, so what was I saying? As I was saying, so again, people are not satisfied with the explanation that J.J. Thomson came up with. So another guy by the name of Rutherford, he decided to probe into basically how the electrons are arranged in atom. And he came up with an experiment, and this is a schematic representation of that experiment. So let me explain what is involved here. Inside here, you have an element which is radioactive, which produces alpha particles. Alpha particles are basically helium-4 nuclei. So basically, an alpha particle is the same as a helium-4 nucleus, all right? So it produces alpha particles which are positively charged. And basically, a stream of those particles are allowed. a stream of those particles are allowed to hit this metal foil, which is a piece of gold material, right? Now, let's think about it. If J.J. Thomson's model, if that were true, right? You'd expect that, okay, since the nucleus is large, according to the model, compared to the electrons, if you hit it with a stream of alpha particles which are positively charged, repulsion will take place and those alpha particles will bounce back, right? That's what you'd expect based on the model put forward by J.J. Thomson. What Rutherford discovered, however, is where's the pointer? Okay, what Rutherford discovered was that the vast majority of particles, alpha particles, pass right through the foil, right? Now, some of them are deflected, and there's a detector that he used, a microscope that he used to detect the presence of those particles. Most of them will pass right through the metal foil. Some of them will be deflected, as shown here, and as shown here, and some of them would be turned back. In other words, going in the opposite direction without passing through the foil, right? So based on what Rutherford observed in his setup, that means that the model put forward by J.J. Thomson cannot work, right? So basically, and again, this is a scientific method at work. You know, when you come up with evidence which conflicts with somebody's model that was put forward, then basically we discard that model, or we make modifications to the model which fits what we observe. And that is what's happening right now. And okay, what's going on with this thing, man? Okay, but I'm still on. Anyway, so basically, oh God. Okay. So basically, based on the observations made by Rutherford in this particular experiment that he designed, he came up with this notion about how the electrons are arranged compared to the rest of the atom. He proposed that instead of having a large nucleus where the electrons are embedded in it, he proposed that the nucleus is actually relatively small compared to the rest of the atom, right? And therefore, as a result, you have the very small nucleus, which is very dense and has most of the mass, and then you have the electrons spreading around the rest of the atom, right? And that explains the observation, because if you think about it, if the electrons are spread around, that means that there's a very great chance that most of the alpha particles will just pass through without coming into any contact or direct contact with any electron. Now, as I said before in the previous diagram, some electrons will be deflected. And that's because electrons like the one in path 3 will come relatively close to the nucleus, but be deflected at an angle, and therefore will pass through but deflect at an angle. And there are a few that will come into direct contact with the nucleus, such as the electrons following path number 4. It comes into direct contact with the nucleus and then bounce back, all right? So this is a better explanation for what is observed in the Rutherford experiment based on his experimental setup. So at this point, the conclusion is the atom consists of a small, dense nucleus, right? And the electrons are basically surrounding, spreading out through the rest of the atom, all right? Okay, so based on Rutherford's experiments, he was able to determine the amount of positive nuclear charges, and it turns out that the amount of charges in the nucleus will be equal to the number of electron charges surrounding the nucleus, right? So these positive charges were called protons, that's how we get that term, and this results in the introduction of the atomic number, which by definition is the number of protons that is present in the nucleus of an atom. So that's where that term was first used, all right? And then in 1932, another scientist by the name of James Chadwick, he discovered the presence of a third particle, right, known as a neutron. And based on what I've read about this discovery, what happened, because I think, let me see here. I think Rutherford did his experiment in 1909, right? So between 1909 and 1932, it was found that there's some sort of discrepancy in that the mass of the atom is not accounted for by just the mass of the protons and electrons, right? So people were curious about, okay, so what accounts for that difference? But it took a while for the third particle to be discovered. And the main reason why is because neutrons were neutral. They had no charge, right? So the type of technology that they had at the time, they were not able to discover the neutrons until James Chadwick came up with an experiment, which I won't even get into, and he discovered the neutrons, which he discovered to have nearly the same mass as a proton, and also it has no charge, right? Let me skip mass spectrometry here. Okay, so that's basically how those particles were discovered. Now, the next thing I'm going to talk about, which might seem unrelated, but it's also very important. And that is wave motion. As soon as I can get this done. Oh, I see why. Hold on. Oh, it is the CF Wi-Fi that's acting. Okay. All right. Okay. All right. So now we're going to talk about wave motion. As I said before, this might not seem to relate to atomic structure, but you're going to see the relationship shortly. So let's talk about wave motion in general. So here we have a picture of a rope being attached to a fixed surface, and somebody is holding one end of the rope and moving it up and down. And I'm quite sure as kids we have played with ropes doing this, and we all know what's going to happen. A waveform is generated that is moving along the rope, right? Of course, we know that what that means is that basically energy is being transferred, but the particles of the rope are simply moving up and down while the waveform is generated, all right? So understanding the characteristics of a waveform, as you're going to see, is very important when it comes to understanding radiation, for one, and how that relates to atomic structure. So there are certain characteristics of a wave that you need to be familiar with. One is called the, before we get to that. So if you understand the waveform that is generated when you move the rope up and down, then that will be important for you to understand the wave nature of electromagnetic radiation, which includes light, right? Because it turns out that you can actually represent the nature of radiation using waveforms, right? Because it turns out that electromagnetic radiation is basically a combination of the fluctuations in electric fields and magnetic fields that are mutual right angles to each other, as indicated in this diagram. So in this diagram, if you imagine a beam of light traveling in this direction, then there are two components to it. You have the electric field, which is moving in this diagram here, represented by the red line, going like this, okay? And then you have the magnetic field, which is at right angle, moving like this, all right? So those two components make up what is known as the electromagnetic wave, all right? And therefore, if you understand the nature of the waveform that I just described with respect to the rope, then you should be able to understand the wave nature of light based on the fact that the actual fluctuations of the electric and magnetic fields is actually a waveform. So there are a couple of characteristics of waveforms that you need to know, or you need to be familiar with. You have the wavelength, the frequency, and to a lesser extent, the amplitude. The wavelength, let's talk about that. The wavelength is the distance between two successive peaks or two successive troughs, or as stated here, two identical points in consecutive cycles, right? I like to look at it in terms of two successive peaks, right? So the wavelength, its unit can be literally any unit of length, meters, centimeters, whatever, right? And traditionally, it is represented by the Greek letter lambda, which is this right here. Lambda kind of looks like an upside down Y.
Professor Nicely.
Okay, so that's a wavelength. The next characteristic of a wave is what is known as a frequency, represented by the Greek letter nu, which looks like a V, or in some textbooks I've seen them use the letter F to represent frequency. And the definition of a frequency is the number of cycles of a wave that passes through a point in a unit of time. And the unit of time is usually seconds. In fact, I don't recall ever seeing the unit of time in this context being expressed in any other unit but seconds, all right? So the actual unit of frequency will be seconds to the -1. So let me just write that down here.
Professor Nicely, can you hear me?
So the unit of frequency will be seconds to the -1, but there's a special symbol and name for that unit. It's called the Hertz unit, Hertz, all right? So that's a Hertz unit, okay? And that will be the unit of frequency that you're going to be using pretty much throughout this particular chapter. And then you have the amplitude of the wave. The amplitude of the wave is basically the distance from a line of no disturbance through the center of the wave peak. And that's pretty much all that I'm going to say about that. The amplitude is actually related to the intensity of the radiation. So the greater the amplitude, the greater will be the intensity. But that's all, as far as I am concerned, that you're going to need to know concerning the amplitude. So therefore, there is a relationship between the wavelength of a waveform and the frequency, and that is given by this equation here. The frequency multiplied by the wavelength is equal to the speed of the wave, all right? So that is true for all waveforms, okay? Including electromagnetic radiation, all right? Now, in the case of electromagnetic radiation, the actual speed of the wave, so let me write this down here. For electromagnetic waves, the speed is equal to a constant value in vacuum, and that would be 3.00 times 10 to the 8 meters per second. And traditionally, we use the letter C to represent the speed of all forms of electromagnetic radiation, including light, right? So it doesn't matter what type of radiation you're dealing with, the speed is going to be 3.00 times 10 to the 8 meters per second. So this here is what is called the electromagnetic spectrum. It's basically a list of all forms of radiation, right, that is known. And in this particular case, it is ordered from left to right in terms of increasing wavelength. Now remember, since C is equal to lambda times nu, and C is constant, right? What that means is that there's an inverse relationship between the wavelength and the frequency, right? So the greater the wavelength, the lower the frequency, and vice versa, right? So basically you can see up here, you have the frequency labeled right here, the frequency values, and down here you have the wavelength. So you see that as the frequency decreases, going from left to right, there's a corresponding increase in the wavelength, right? So the different forms of radiation are indicated in different blocks here. So gamma rays, one form of radiation, their frequencies go from somewhere here, which looks like 10 to the 20, I don't know, 23, to about here, which looks like 10 to the, I don't know, maybe 19. And then X-rays fall within this range. And then you have ultraviolet rays, right? And then after that, you have a narrow band right here. In that narrow band, we have the visible part of the electromagnetic spectrum. So here we're talking about the different colors of light, all right? There is a memory aid that I use to remember the order, Roy Biv. I don't know if this would help you. Red, orange, yellow, green, blue, indigo, violet, going in the other direction, right? So this is in order of increasing frequency. All right, increasing frequency. All right, and I remember reading years ago that among human beings, only the females of the species can determine the difference between indigo and violet. And I'm more inclined to believe that to be true because I cannot tell the difference between indigo and violet. All right, so that's something interesting. So, okay. So that's a narrow range right here where the different colors of light exist, right? And then just after that, you have infrared, then you have microwave, and then you have all the radio waves here talking about the frequencies associated with the radiation when it comes to cellular phones, AM radio, FM radio, and so on, TV. And then you have what is called the extra low frequency part of the spectrum, right? So that's basically the electromagnetic spectrum, okay? All right, so let's see here. So as I said before, all forms of electromagnetic radiation show wave-like and they travel at the same speed. As I said before, the speed they all travel at is 3.00 times 10 to the 8 meters per second. Okay, so that's the electromagnetic spectrum. Now, we're going to pay attention to the visible part for a minute. We're going to look at this setup right here. So in this setup, what we have here is a light source. And basically, we have this placed in front of the light source so that a beam will pass through, and then that beam will be allowed to pass through a prism. Now, the prism will be made up of some transparent material like glass or plastic, right? Now, what's going to happen is that the white light source will basically separate into the different colors of light, right? And it does so as it passes through the prism by a process known as refraction. Refraction is basically, and again, this is something I remember learning in physics. Refraction is basically what happens when a light beam passing from one medium to another bends, right? And that is as a result of a change in the speed, all right, of the light, okay? This thing keeps happening. And I have another class coming after. I hope this doesn't continue to occur. Same Wi-Fi crap. Okay, see what's if I'm back in business yet again. Okay. Okay, so as I was saying in this setup, refraction is taking place, and it turns out that the different colors of light will be refracted to different extents. So therefore, as a result, the white light will separate into different colors. It will pass through here, emerges from the other side, and then projected onto a screen. And then what you're going to get is basically the visible part of the spectrum displayed on the screen, right? And we call this a continuous spectrum, right? Basically continuous because as you go from one end to the other, you see the colors kind of running into the other one without any clear line of demarcation between the different colors, right? So that's the continuous spectrum that is formed, which basically indicates that white light is basically a combination of all these different colors of light, all right? Now, that's a continuous spectrum, and each of these forms of radiation will have different values for their wavelengths and frequencies. So what is shown here are the approximate wavelengths for the different colors that you see here, right? Okay, so that's a continuous spectrum. Now there's another type of spectrum known as the line spectrum, which is not continuous, right? And this is used, or this is produced, I should say, based on an experimental setup where an element undergoes electric discharge, right? And it produces radiation, it produces light, and then that light is projected onto a screen, as you can see here. Now, what we have in this particular tube is hydrogen gas at a very low pressure. And then that lamp is connected is connected by two wires to an external electricity source. You flip the switch, and then it starts to glow. And then that light is projected through a slit, through the prism, and then the different colors of light separate out and projected onto the screen. And what you're going to see is not a continuous spectrum, but what we call a line spectrum, where you have different colors of light being shown on the screen. So I don't know if you can see it from where you are, but this here looks like purple or indigo or violet, whatever you want to call it. And then I think this is almost the same color. You have blue, and then you have red here, and that's it. And of course, you see some dark regions in between, right? So it turns out that different elements under these same conditions will produce different line spectra, right? And understanding how these line spectra are formed is key to understanding how the electrons are arranged in the atom, all right? So that is what is produced in the case of hydrogen. And I think I have some others here. Okay, and these are other elements, line spectra, mercury, lithium, cadmium, and strontium, right? And in fact, you might find this interesting. The reason why astronomers know that there are certain elements that exist, for example, in stars, like the sun, they have instruments where they can determine the line spectra. And because each element has its own unique line spectra, they can tell, for example, that iron exists in the sun as a gas, all right? Because they have the line spectrum. They can determine the line spectrum of iron from the sun, all right? So these are just some examples of line spectra. Each element has its own spectrum, and that's why it's considered to be the fingerprint, quote unquote, for the respective elements, all right? Okay, what time is it? All right, let me just quickly go through this idea of black body radiation, all right? So another scientist, I think he's from Germany, he proposed that vibrating atoms in a heated solid could absorb or emit electromagnetic energy only in small, discrete amounts, all right? And he determined that the energy of that particular electromagnetic energy that's emitted or absorbed can be calculated using this formula. E is equal to h nu. Now, E is the energy, nu is the frequency. What is h? H is a constant known as Planck's constant, and this is a value right here, 6.626 times 10 to the minus 34 joules second. For all purposes, we're just going to run it out to 6.63, all right? Times 10 to the minus 34, okay? And basically, according to his hypothesis, the energy that is absorbed or emitted can only be emitted or absorbed as what we call a quantum, represented by this formula, or as whole multiples of a quantum. All right, so that's what he proposed. All right, I'm going to stop there for today, and then we're going to continue our discussion of chapter 6. Let me just say that I'm in the middle of grading your assignment number 5, right? So what I'm going to do, in fact, let me do this now. I'm going to post the answer key so that you have that at least to to review, because remember your test is, when did I say?
This Monday.
Monday, right? So, let me, before I forget, knowing me, I'm going to publish assignment number 5. I'm sorry, I'm going to publish assignment number 5, answer key. Oh, I think it's already public. Oh, it's already public. All right, so you can have that to review in preparation for your upcoming test, all right? And then I'm hoping to finish grading your assignment 5 by this evening, and then I'll send it to you, and that's it. Okay, for you guys out there in Zoom, I'm gonna